Hello friends, welcome to today's lecture. Here in today's lecture we will continue with the previous lecture. In previous lecture we have defined the concept of variational derivative, and as an application we have shown the invariance of the Euler's equation. So in today's class we will discuss some example of invariance of Euler's equation, and we try to discuss the problem which is known as isoperimetric problem. So here we start. So here if you recall, we have discussed the concept of variational derivative, and then we have discussed the invariance of Euler's equation, and now we are moving to the first example based on invariance of Euler's equation. So the example is given by this. So here we have J of R, and which is given as some phi 1 to say phi 2 under root of r square plus r dash square d of phi here, and here we want to minimize, we want to extremize the functional given here. So here your r is given as r of phi here, where so here this actually represent the distance between say two say r1 and phi 1 be one point, and r2 phi 2 is another point, and this represent the arc element with joining these 2 points. Let us call this as point A and B, and this simply represent the length element ds here. So here we want to we can consider here that in polar coordinate system we want to find out say the curve which minimizes the distance between these 2 points A and B. So for that we are trying to find out, so we are extremizing this functional. So here your ds is given as say r square ds is equal to dr square under root r square d phi square. So which we can represent as say dr d phi whole square plus r square, which is nothing but d of phi. So which is nothing but r square plus r dash square d of phi. So basically this represent what j of r is equal to say phi 1 to phi 2 ds here, ds by d phi and d phi. So basically we want to extremizing this functional given in here. So here we want to find out say this, the minimum distance between A and B along the curve r here, r equal to r of phi here, right. So if you look at with the help of invariance of Euler's equation in this particular in form, your this f is given as function of phi r and r dash, and in this case your Euler's equation is written as f of r minus d by d phi of f of r dash equal to 0. So if you want to find out the Euler's equation will be what? Euler's equation will be, here you can write it 1 upon 2 under root r square plus r dash square, and here we have 2 of r minus d of phi, and this is what here we can write it 1 upon 2 under root r square plus r dash square, and when you differentiate this you will get 2 of r dash, and that is equal to 0. So here we can simplify this and we can get this is r upon under root r square plus r dash square minus d by d phi upon r of r dash upon under root r square plus r dash square, that is equal to 0. So to find out say extremizing curve for this functional, we need to solve this particular equation, which is r upon under root r square plus r dash square minus, to find out say derivative of this we use the formula for derivative of f by g. So here we have r square plus r dash square, and here we have under root r square plus r dash square, and derivative of r dash, that is r double dash, minus r dash and then derivative of this, that is 1 upon 2 under root r square plus r dash square, and then we find out the derivative of this here. So that is it is 2 r dash plus 2 r dash r double dash. So that we are writing it here. Okay. So that is equal to 0. So to simplify this, let us simplify this here. So here we can simplify this as r upon under root r square plus r dash square minus, if you take the this under root r square plus r dash square, multiply by that and simplify, you will get r double dash multiply by r square plus r dash square minus r dash, and if you simplify these two will be cancelled out here, we will get what, r dash into r dash plus r dash r double dash, and this will be, and in denominator we have r square plus r dash square into r square plus r dash square root of this, that is 1 by 2, and this is equal to 0. Then we can take this thing in denominator and you can say that it is r into r square plus r dash square minus, you simplify this, here when you simplify you will get r square r double dash minus r dash square r double dash plus r dash square r, then here we will get plus r dash square r double dash equal to 0. So we can say that this will be satisfied if the numerator is equal to 0. Now if you look at, is there anything which is cancelling out? So here if you look at r dash square r double dash, this will be cancelled out here. So we have this thing. So this represent r cube plus r dash square minus r square r double dash plus r dash square r has to be 0. So dividing by say r dash throughout, we can say that r square plus r dash square minus, so here this is we divide by r here, so it is r square, this and this term are same, so we can add them and we can divide by r, so 2 r dash square minus r double dash is equal to 0. So if you simplify a little bit further, take it on the other side, we have r double dash minus 2 r dash square minus r square is equal to 0. So the Euler's equation in this particular for this particular functional is given by this, which is quite difficult to solve here. Here r dash is your dr by d phi. So what we try to do here, we try to use the take the help of invariance of Euler's equation and try to find out a new coordinate system where this equation is solvable. So for that, what we try to do here, we use the change of variable, that is x equal to r cos phi and y equal to r sin phi. So what we try to do here, in place of polar coordinate system, we want to find out in a we want to consider the same problem in a rectangular coordinate system. So here we take x equal to r cos of phi and y equal to r of sin of phi. So to find out the equivalent this thing, so you simply find out dx by d phi, so which is given by say minus r sin phi plus your r dash, you can write it here as cos of phi d phi, so d phi, and here similarly you can find out dy by d phi, so that is r cos of phi plus r dash, and here you can get this is y dash r cos of phi plus r dash sin of phi d phi, right. So it means that new coordinate system, that is xy coordinate system, we have j1y is equal to the corresponding, let us say phi 1 is given by x1, so and phi 2 is corresponding to say x2, and this under root r square plus under root r square plus r dash square is given by under root say dx square plus dy square, and so this can be written as x1 to x2, and this is 1 plus dy by dx whole square and d of x here. So it means that this functional is now reduced to j1y, and your integrand is under root 1 plus dy by dx whole square d of x. So here your f of x y dash is given by under root 1 plus y dash square, and which is quite easy to solve. In fact, we have already solved here. So here your Euler's equation is given by f of y minus d by dx of f of y dash is equal to 0. So here there is no y term here, so will be 0 minus d by dx of f of y dash, that is 1 upon 2 1 plus y dash square 2 y dash here is equal to 0. When you can solve this, you will have d by dx of y dash upon under root 1 plus y dash square equal to 0. And when you solve this, in fact this we have already solved somewhere, then this is coming out to be solving y double dash is equal to 0, which is nothing but y of x is equal to c1x plus c2 here, where c1 and c2 are integration constant, that you can find out with the condition that your y of x1 is equal to y1 and y of x2 is equal to some y2. So with the help of these two condition, you can find out c1 and c2, and you can say that the extremal for this functional is a straight line. So here we can say that the extremal of this functional is given by say r sin phi is equal to c1 r cos of phi plus c2. So it means that here though it is the Euler's equation, if we consider here, is quite difficult to solve, but if we use the change of coordinate system and the property that is change of invariance of Euler's equation, we have converted this functional into a new functional which is quite easy to solve, and with the help of Euler's equation in new coordinate system it is quite easy to solve, and here our extremal curve is coming out to be straight line satisfying the these two condition. And if you consider the original functional, then the extremal curve for this functional is given by r sin phi equal to c1 r cos phi plus c2, which is quite difficult to solve in the in a polar coordinate system r and phi. So here what we have discussed here. So this functional is reduced to this x0 to x1 under root 1 plus y dash square d of x, and the corresponding Euler's equation given by this, and which have solution y equal to c1x plus c2. This is just now we have proved, and extremal for the functional which is given here is given by r sin phi equal to c1 r cos phi plus c2. Now let us move to second example, and the example here is to find out the extremal of j of y of x, which is 0 to log of 2 e to power minus x y dash square minus e to power x y square d of x, which is given in terms of rectangular coordinate system xy. So here your, if you look at the integrand is e to power minus x y dash square minus e to power x y square. So if you want to find out the extremal, so we know that extremal must satisfy the Euler's equation, which is given by f of y minus d by dx of f of y dash equal to 0. So if you calculate say fy is nothing but minus 2 e to power x y here, and f of y dash will be 2 of y dash e to power minus x, and when you simplify you will get this equation y double dash minus y dash plus e to power 2x into y equal to 0. So it means that if y is a extremal of this functional, then it must be a solution of this second order differential equation. Now if you look at this second order differential equation, y double dash minus y dash plus e to power 2x y equal to 0. Here we do not know any general method to solve this particular problem, though we can solve this particular problem by changing the independent variable, by saying that e to power x equal to a new independent variable that is t. Then we can solve this, we can convert this problem into a second order differential equation with a constant coefficient in terms of independent variable t, and we can solve it. But we can avoid that, and we can say that this can be simplified further if we take x as log of u and y equal to v. In fact, we can say that e to power x as a new variable, that is u, and y as simply v. So here we have written the functional given in this form. Now let us assume that e to power x is equal to u, and here y is given as v. So here I can write x as ln u and y as v. Then we try to find out, say, this functional in terms of u and v. So it means that we want to find out g v1 of u. So here let us find out, say, limit of u here. So limit of u will be what? When x equal to 0, then u is given as 1, and when x is equal to log of 2, so it means that when x equal to 0, then this represent u equal to 1. When x equal to log of 2 base e, then this represent this will give you u equal to 2. So limit for u will be 1 to 2, then e to power minus x will be, say, 1 upon u. Now y dash square will be what? So we have to calculate what is y dash. So y dash will be dy by d of x. So dy is given as say y u du plus y v dv divided by x u du plus x v dv. So everything is given here. So y of u will be 0 here. So we can write this as, we can further simplify this as dy by dx as, this is y u plus y v v dash x u plus x v v dash. So here y of u will be simply 0 plus y of v will be 1. So this is v dash, and x of u will be say 1 upon u, and x of v is 0 into v dash. So here we will give will have dy by dx is equal to, so this will go up and it is u v dash. So dy by dx is given as u v dash. So 1 upon u, and here we have u v dash square of this minus this is e to power x as u and y square as v square, and d of x is given by, here you can find out dx as 1 upon u d of u. So it is d of u on u. So you can simplify it further, it is 1 to 2, and when you take when you multiply u inside, then it will be what? So you can say that 1 upon u square, and this is u square v square u square v dash square minus this will cancel out here, and we have v square, and this is du. So this is nothing but 1 to 2, this is v dash square minus v square and d of u. So it means that this functional is now reduced to new functional which is given as j1 v of u, and here your integrand is v dash square minus v square. So now if you want to find out, say, extremal of this functional, then we can apply your Alice equation in new coordinate system, and here you can say that it is what? f1 of v minus d of du f1 of v dash equal to 0. So f1 v will be, so minus 2 of v minus d of u, and f1 v dash will be 2 of v dash is equal to 0. And when you simplify this, this is what? Minus 2 of v, and this is minus 2 of v double dash is equal to 0, and which is nothing but, so here we have v double dash plus v equal to 0, which is a very simple second order differential equation with constant coefficient, and the solution is given as simply c1 cos of u plus c2 sin of v. So let us look at here in the slides. So here we have just seen that this functional, this j of y of x can be written as I1 v of u, that is 1 to 2 v dash square minus v square d of u. Here your integrand is v dash square minus v square, and then we can find out the Euler's equation in new coordinate system as f of v minus d by du of f of v dash equal to 0, which is coming out to be v double dash plus v equal to 0, and the solution is given as v equal to c1 cos of u plus c2 sin of u. And if we convert into the original functional, then our extremal is given by y equal to c1 cos of e to power x plus c2 sin of e to power x. So here if we start with the original coordinate system, that is xy coordinate system here, then Euler's equation is this, which is a little bit difficult to solve it here, but if we change the coordinate system, then we have seen that it is very easy to obtain the extremal curve in new coordinate system. So that is the very useful application of invariance of Euler's equation. Now we will move to next problem, that is isoperimetric problem. So what is isoperimetric problem? This is a very old problem. So in isoperimetric problem we have to find out that among all the closed curves with a given length, say some given length, say let us say L, we need to find out the curve which encloses the maximum area. So it means that we have to find out a curve with the fixed length, means parameter is fixed, then we want to find out say the curve which have a maximum area, and answer is also known from the very beginning, and it is coming out to be a circle, but how to prove it, we will try to prove it here, a new problem which is known as isoperimetric problem. Here what we try to do here, we want to find out the curve y equal to y of x, for which we extremize this function which is given as j of y between equal to a to b f of x y y dash dx, has with the boundary condition y of a equal to a, y of b equal to b, provided that the other condition which is given in terms of functional integral here, that I of y a to b g of x y y dash dx remains as a constant. So it means that the problem is what, we need to extremize the functional this, provided that this value remains constant. So among all the function for which it is true, we want to find out the curve which extremizes this function. So to solve this problem, we assume here that the function f and g have continuous first and second derivative in entire interval a b for arbitrary values of y and y dash, and then we have the following theorem. So to find out the extremal of this problem, to extremize a function given another function take a constant value, we have the following theorem which says that consider the functional j of y which is given as a to b f of x y y dash d of x satisfying the condition y of a equal to a, y of b equal to capital B, and the integral I functional I y which is given as a to b g x y y dash dx take the value L, and we want to say that if j y have an extremum for y equal to y of x and y equal to y x is not an extremal of the other functional, that is I of y, then there exists a constant lambda such that y equal to y of x is an extremal of the functional a to b f plus lambda g d of x. It means that this y equal to y x is extremizing this functional. It means that this functional f plus lambda g, this integrand f plus lambda g satisfy the Euler's equation which is given as f of y minus d by dx f of y dash plus lambda gy minus d by dx of gy dash equal to 0, or in other word we can say that if f is denoted by f plus lambda g, then f satisfy the Euler's equation at every point of x in this interval a to b. So that is what is the theorem, we want to prove this theorem. So to prove this theorem we use the concept of variational derivative. So here let us consider the proof here. So let jy have an extremum for the curve y equal to y of x. subject to the condition that the extremal the other functional have a constant value, that is L. Now to find out that, let us choose 2 point x1 and x2 in the interval a b, where x1 is arbitrary and x2 is also arbitrary, but satisfying certain condition which we will discuss later on. The idea is that whenever we try to find out, say that y of y equal to y of x is an extremum curve, we try to find out, we perturb the curve y of x and try to see the functional value for those perturbed curves. And here we cannot do arbitrary perturbation as we have done while proving the Euler's equation, while finding the Euler's equation. Here if we change a little bit this y of x, then it may happen that the value of this functional will also change. So it means that if we take in place of y as some other curve, say y1, then it may happen that this I of y will also change. So here we have to keep this thing in mind, that we can consider only those perturbation of y. Perturbation means deviation from y such that this remain constant. So here what we try to do here, let us consider an increment in y of x given by delta y1 x plus delta y2 x, where delta y1 delta 1 yx is non-zero only in neighborhood of x1 and delta 2 yx is non-zero only in a neighborhood of x2. So if we change delta 1 y of x in the neighborhood of x1, then it may happen that your value of the I will also change. To balance that, we consider another point x2 where we take another variation in y of x, which is given as delta 2 y of x, such that your value remain constant. So using variational derivative, let us see how it is, how we can write in terms of mathematical symbols. So using variational derivative, we can write the corresponding increment delta j of the function j in this form. So here delta j is given as delta j by delta y given at x equal to x1 plus epsilon 1 delta eta 1 plus delta j upon delta y given at x equal to x2 plus epsilon 2 delta y2. So here if you remember, they are only change in the neighborhood of x1 and in the neighborhood of x2. So here delta j is given in terms of variational derivative at the point x equal to x1 and the point x equal to x of 2. So here delta eta 1 is the area of the curve between a to b, delta y1 delta 1 y of x dx, and delta eta 2 is the area area of delta 2 y of x between a to b dx, and as epsilon 1 epsilon 2 tending to 0 as delta eta 1 and delta eta 2 tending to 0. So as this delta eta 1 and delta eta 2 tending to 0, then these epsilon 1 and epsilon 2 will also tend to 0. So now we have a perturbed curve which is given as y of x plus delta 1 y of x plus delta 2 y of x, and then for this we try to find out, say that I of y will remain invariant, means remain constant. So I of y will be given as I of y star. So for this we find out, say increment in delta I in terms of variational derivative, which is given as delta I is equal to I of y star minus I of y. Since both are same, it has to be 0. Now this can be written as in terms of variational derivative as delta I by delta y at x equal to x1 plus some epsilon 1 dash into delta eta 1 plus delta I by delta y evaluated at x equal to x2 plus epsilon 2 dash into delta eta 2. So here delta eta 1 is given by this area and delta eta 2 given by this area, and epsilon 1 dash and epsilon 2 dash will tend to 0 as delta eta 1 and delta eta 2 tend to 0. So here this will give us a condition that how this delta eta 2 is given in terms of delta eta 1. So from this last equation 14 we try to find out delta eta 2 in terms of delta eta 1. For this we assume that we choose our x2 to be a point for which delta I by delta y at the point x equal to x2 is non-zero. But how it can happen? This will happen because by hypothesis we have already assumed that this y equal to y of x, which is an extremal of the functional j, but it is not an extremal of the functional I. So, with this choice we can say that delta eta 2 can be written as minus of delta I by delta y given at x equal to x1 divided by delta I by delta y given at x equal to x2 plus epsilon dash into delta eta 1. Here as delta eta 1 is tending to 0, your epsilon dash is also tending to 0. Let me write it here and then we can understand it in a more better way. So, we know that delta eta 2 given by this ratio delta I by delta y given at x equal to x1 divided by delta I by delta y x equal to x2 plus epsilon dash into delta eta 1. This we have obtained from the relation that delta I is equal to 0. So, when delta I is equal to 0 means this quantity is equal to 0, and since we have assumed that this y is not an extremal of non-zero at any point between a to b. So, it means that delta I by delta y at the point x equal to x2 is non-zero. So, using this value here we can find out delta eta 2 in terms of delta eta 1, and it is given by this thing. Now, if you use delta eta 2 here in the functional in this value delta j is equal to this thing, then your delta j can be written as, let me write it here. So, here you can say that delta j is given as, in fact this is not this is delta j. So, here delta j is equal to, you can say delta j upon delta y plus epsilon 1 into delta eta 1 plus here you have delta j delta y at x equal to x2 plus epsilon 2, and here delta eta 2 I am writing it like this, delta I by delta y at x equal to x1 divided by delta I upon delta y given at x equal to x2 plus epsilon dash into delta eta 1. So, when you simplify you can write here this, when you simplify you will get delta j by delta y, and this quantity we are assuming here, this quantity divided by this quantity as lambda. So, here we are assuming lambda as delta j upon delta y evaluated at x equal to x2 divided by delta I by delta y evaluated at x equal to x2 as lambda. So, if we assume this, then here we have lambda delta I upon delta y evaluated at x equal to x1, this is already x equal to x1, this is at x equal to x1 plus some epsilon tilde into delta eta 1. So, here your delta j is given in this particular form. So, please if you look at here we have removed the component x equal to x2 and delta j is given by this, where epsilon tilde is something which is tending to 0 as delta eta 1 is tending to 0. So, here using this we can write delta j as this. So, now where as delta eta 1 is tending to 0, your epsilon is tending to 0. So, this expression for delta j explicitly involved variational derivative only at x equal to x1, and the increment hx is now just delta 1 yx, since the compensating increment delta 2 yx has been taken into account automatically by using the condition delta I equal to 0, that we have taken to find out delta eta 2 in terms of delta eta 1. So, it means that the first term in the right hand side of this equation 16 is the principal linear part of delta j. So, delta j is given by this. Now, here this term is tending to 0 as delta eta 1 is tending to 0. So, it means that this will give you the variation of the functional j, and we already know delta, so it means delta j is equal to this quantity. Now, we know that necessary condition for an extremum is that your variation is equal to 0. Now, here delta eta 1 is non-zero while x1 is arbitrary, we can say that this is equal to 0 for all the point between a to b. So, it means that delta j by delta y plus lambda delta I by delta y is equal to 0 for all x. Now what is delta j by delta y? It is fy minus d by dx of fy dash, and delta I by delta y is gy minus d by dx of gy dash. So this gives you a condition which is precisely the condition which we want, that this we have that f is the extremal of the functional j, provided that the extremal I will have a constant value. We have the condition imposed on y is this. So here we have discussed the generalized isoperimetric problem, which is this, that we want to extremize the functional jy here, provided the other functional keeping the constant value. So we have proved the following theorem, which says that if you want to extremize the functional jy equal to a to b f of x y y dash dx, and y is the extremal of this function, provided that this value of this function is constant, we have just shown that y equal to y of x is an extremal of the functional a to b f plus lambda g dx. It means that if we denote this integrand as capital F, then this capital F satisfy the Euler's equation. So so this gives you an idea to extremize a function such that your extremal curve satisfy the other extremal keeping as a constant value. So in next class we will discuss some example based on this. So here we stop with this note only, and meet in next class. Thank you very much for listening us. Thank you.